Oh. Oh, hey there. I'm looking through more of the pictures I took during my last trip to the amusement park. You may recall that recently we found a function that represented the velocity of the sky plunge, and today I'm thinking about the Ferris wheel. A Ferris wheel follows a fascinating pattern of motion as the cars rise and fall in a repeating cycle. I wonder if there's a way to represent the motion of a Ferris wheel using a graph and equation. Let's explore the motion of a Ferris wheel in more detail. Look at the diagram labeled number 1 in your guided notes. This wheel has a diameter of 60 meters and its center is 35 meters above the ground. It completes one full revolution every 4 minutes. Take a moment to label the key points on the diagram using this information. Imagine yourself in one of the cars as it rotates around the wheel. You start at the lowest point, where your height above the ground is at its minimum. Then, as the wheel turns, you smoothly rise to the highest point at the top before coming back down again. Find the table in number 2 of your guided notes and calculate the height of the Ferris wheel car at each given timestamp. Then, in number 3, plot those points on the axes provided and record any observations or predictions you have. Did you notice any patterns or familiar shapes after plotting the 9 points from the table? I think I'm starting to recognize something. Let's compare the motion of the Ferris wheel to the graph to be sure. Let's start by tracking a car starting at the lowest point. It rises smoothly to the midpoint in 15 seconds, then continues up to the top before beginning its descent. Once it reaches the bottom, the cycle repeats. By mapping the height of one Ferris wheel car over time, we see a familiar sinusoidal function emerge. Sinusoidal functions are periodic functions that smoothly oscillate between minimum and maximum values, just like the sine and cosine curves we've studied. If you haven't already, go ahead and connect those points in your guided notes with a smooth curve. And then we'll work together to write an equation for this function. Now that we've seen how the motion of a rider on a Ferris wheel can be modeled by a sinusoidal function, we want to write an equation modeling that function. This graph we've drawn could be modeled by either a sine or a cosine function, and before I begin finding its features, I like to start by asking myself whether my function is more similar to a sine function or a cosine function. Which one do you think is closer? I notice that our Ferris wheel function has a minimum point on the y-axis, while the parent cosine function has a maximum on the y-axis. That means that if we write a cosine function, we'll need to write a reflection, but we won't need to worry about a phase shift. Now that we've determined that we'll write a cosine function, try writing the equation on your own. Start by determining characteristics like the amplitude, period, and midline, and filling in the table. And remember, when filling in this table, you don't have to go from top to bottom. You can start wherever it makes sense to you. Okay, let's check and see how you did. We already know that we are writing a cosine function with no phase shift, so c will be 0. The next thing I found was the function's midline. The midline is always halfway between the minimum and maximum values, and it represents the vertical shift. Sometimes, it's easy to find a function's midline by looking at the graph, but we can also find the midline by calculating the average of the minimum and maximum values. 65 plus 5 divided by 2 gives us 35, so the midline is y equals 35, which means that the value for d in our equation will be 35. Now let's find the amplitude. The amplitude is the distance from the midline to a minimum or maximum point. The midline is 30 units below the function's maximum value, so the amplitude is 30. But before we move on, remember I said I'm writing a reflection of the cosine function. So what does that mean for a? Correct! A will be negative 30 because this cosine function has been reflected. We're almost there. What's missing? Right, the period, which helps us find b in the equation. Remember, b is related to the function's period, but it isn't the period itself. B represents the number of cycles over 2 pi, and we find it by dividing 2 pi by the period. In this function, the x-axis is measured in whole numbers instead of multiples of pi, but our approach stays the same. We still divide 2 pi by the period to find b. What is the period of our Ferris wheel function? Right, it was 4 because the Ferris wheel takes 4 minutes for 1 revolution. So we divide 2 pi by 4, giving us b equals pi over 2. Now we have everything we need, and therefore, one way to write a sinusoidal function to this Ferris wheel is y equals negative 30 cosine of pi over 2x plus 35. Notice I said that cosine was one way to write this function. What if we wanted to write it as a sine function instead? Remember, for a general sine function, the midline crosses through the y-axis, so I could also visualize the Ferris wheel function as a non-reflected sine function that's been shifted 1 unit to the right. Take a moment to think about which characteristics and parameters would change from the cosine function and which ones would stay the same. If we write a sine function for the Ferris wheel ride, the amplitude, period, and vertical shift don't change. What about the parameter for a? Since this function is rising as it passes through the y-axis, just like the parent sine function, we can write a as positive 30 so that the function is not reflected. As we said a moment ago, the Ferris wheel function is shifted to the right 1 unit, so in this case, c is 1. It's important to remember that when we have both a b and a c value, b must be placed outside the parentheses that enclose x minus c, so our equation should look like this. Y equals 30 times sine of pi over 2 times x minus 1 plus 35. Great work so far! There are so many periodic real-world situations that can be modeled with sinusoidal functions. Let's try another one. As part of their research, oceanographers often track the height or depth of the tide. At a marine research facility, oceanographers began measuring the ocean's depth at a certain location at midnight. High tide occurred at 2 a.m., at which time the water was 62 feet deep. 6 hours later, low tide was measured to be 56 feet deep. Write a sinusoidal function modeling the tide's depth as a function of time. Okay, I don't know about you, but it can be tricky to know where to start a problem like this. Sometimes it seems like I don't even have enough information. How will I write an equation modeling the tide? Before trying to write an equation, I always like to start with sketching a graph so that I can visualize the situation. Drawing a graph or plotting any points we do know is often a great way to get started on a problem. There are some guidelines when it comes to plotting an unknown sinusoidal function. Let's take a look. Whenever you graph an unknown sinusoidal function, try plotting 5 key points to outline one full period: maximum, midline, minimum, midline, and back to the maximum. This gives you one full period, which you can repeat to graph the entire function. What if you don't start at the maximum? No problem. You can still plot points at the function's midline, minimum, midline, maximum, and midline. As long as your points include one maximum, one minimum, and return to the starting y value, you've defined one full period. And do you notice anything special about the spacing of these 5 points? Together, they divide the function's period into 4 equal sections. That's a key concept that will help us graph our tide problem, so let's look at it again. We know that high tide occurred at 2 a.m. and was 62 feet deep. Let's see what that might look like on our diagram. At 2 a.m., the water was 62 feet deep. Then, 6 hours later, low tide was measured to be 56 feet deep. Before we try writing the equation, let's see if we can plot a sinusoidal function modeling the tide using the 5 key points. The information we are given will help us with 2 keys, the minimum and maximum. We are also given that the 2 quantities being measured are time and depth. So let's start a graph where the x-axis measures the number of hours after midnight and the y-axis measures the water's depth in feet. At 2 a.m., the water was 62 feet deep. That gives us a maximum of 62. 6 hours later, the water was at its minimum depth of 56 feet. What time was that? Right, it was 8 a.m., so we can plot a point at 8:56. We'll also need to know where the midline is in order to graph our 5 points. Try doing some mental math. What would be the time and the water's depth at the point between the maximum and minimum? At 5 a.m., the tide reached its midpoint of 59 feet. Let's take stock of what we've done so far. Oceanographers have observed that it takes 12 hours for a full cycle of tides to go from high tide to low tide and back to high tide. 1/4 of that 12-hour cycle is 3 hours. That means that every 3 hours on our x-axis, we can plot another of those 5 key points we looked at earlier. So far, we have high tide, the midline, then low tide. Next, we'll go back to the midline, and finally, back to high tide again. And there are the 5 key points that delineate one full period of the function. Pause the video here and use your guided notes to plot this function on the coordinate plane provided, and then write an equation that represents it. If you feel up to it, challenge yourself to write the equation as both a sine function and a cosine function. Let's see how you did. Connecting our 5 key points with a smooth curve and continuing the pattern gives us a tide graph that looks like this. Now let's try writing 2 equations for this function. Let's start with a cosine function first. The function's amplitude, or height above the midline, was 3 feet, so a equals 3. The period was 12, since that's how long it takes to complete one full high tide, low tide cycle. We find b by dividing 2 pi by 12, so the b value is pi over 6. Since we're writing this as a cosine function, we should note that instead of having a maximum on the y-axis, the maximum has been shifted 2 units to the right, so c is positive 2. Finally, the midline of the tide was at 59 feet, so d is 59. This gives us the function y equals 3 cosine of pi over 6 times x minus 2 plus 59. Great work! As our final task today, let's also write this as a sine function. Which characteristics would be the same if we write the tide function as a sine function? Right, the amplitude, period, b, and vertical shift, along with d, don't change. However, to write this as a sine function, look closely at the relationship between points on the function's midline and the y-axis. I noticed that a point on the function's midline was 1 unit to the left of the y-axis, so I wrote the phase shift as a shift 1 unit to the left, which means that for a sine function, c would be -1. That gives us a sine function of y equals 3 times the sine of pi over 6 times x plus 1 plus 59. Let's take a look at our key takeaways for today. Sinusoidal functions can model many different types of real-world phenomena, like tides and oscillating motion. We can apply transformations to adjust amplitude, period, phase shift, and vertical shift. And given a description, we can write and graph the corresponding sine or cosine function. Now that you've watched this video and completed your guided notes, be sure to complete any additional lesson activities to prepare for the wrap-up assessment, and I'll see you next time.
Hey, hey.